Hello, this is Jack Jackson. In this video, we're going to talk about some properties of the Cartesian graphs of the 6 basic trigonometric functions, that is sine, cosine, tangent, secant, cosecant, and cotangent. And in the last video and previous videos, we looked at how we could take the definition of those functions, which comes from circles centered at the origin, or angles in standard position, and we took that unit circle representation and then from that got a Cartesian graph representation. For example, for a sine graph, that turns out to be a wave in the Cartesian representation. And what we're going to do in this is look at those Cartesian graphs and talk about what their properties they are, and we'll connect it back to the unit circle graph as well, but mainly we'll be focusing on the Cartesian graphs and look at the characteristics of those functions. But before we do that, let's look into some notation. One of the things that is most interesting about trigonometric functions is that they are periodic, right? And so that they have a repeating pattern over and over and over and over again. So for example, if you have a particular x value, there's exactly one y value because they are functions. But if you have a y value, there are multiple x values that give you that same y value. Not just one or two or three or 100, but infinitely many that give you the y values. So if a y value actually shows up, it shows up infinitely many times on the graph. So when we start talking about their characteristics, uh, we have to start talking about infinite sets. For example, if we start talking about what are the x values uh, of the points where the sine crosses the x-axis, or what do we talk about those ordered pairs of points, there are actually infinitely many of them. So we need to come up with some way to represent this infinitely many things. It's not just anything, but there are infinitely many of them. And we want to do this using some mathematical notation. So I want to make sure you understand the notation. So specifically, if we're looking at the set of points ordered pairs, their coordinates, where the sign of the input is 0, these look like this. Okay, they are ordered pairs. So that's parentheses with a comma. The second coordinate is 0 if it is on the x-axis. And then the first coordinate looks like some number times pi, where that number is an integer. This vertical line is such that this says the n is an element of the set of integers, and the little curly braces include the whole thing in what's called a set. So this is a whole set of ordered pairs that are that make up the x-intercepts for the sine function. So first of all, make sure you understand some of the different pieces of this, okay, that okay, so this symbol right here is an element of. This is the set of integers. If you're drawing this symbol by hand, you do it like this. A horizontal piece, slanted, then a slanted piece. Okay, then you start over here, do a parallel slanted piece, and come on, and then go across this way. So something like that. It's kind of sloppy, but that's basically how you do that. That's the set of integers. Of course, the set of integers are 1, 2, 3, 4, forever. That's the natural numbers. Also 0, the whole numbers, and then their opposites. So those are the set of integers. So YZ, that's comes from German. Zahlen is the German word for number or integers there. Okay. And so the x's are just an integer times pi. So we see that here's another way of writing that same set, right? It's It's 0 when n is 0. Well, I'm sorry, that's not the set. That's just the set of the first coordinates. So if I fix it like this, where that's just the n pi, this is that. And that's the first coordinates there. So just want to make sure you understand that notation. It's a compact way of doing that. We would say this is all the set of n pi, or n times pi, such that, the vertical line means such that, n is an element of the set of integers. So that's how we could read that. And this is what it's just a shorthand notation for writing this infinite set. Okay, so with that in mind, we can go forward with our examination of properties of graphs, trig functions. Okay, so now let's look at this GeoGebra applet that I've built for looking at the graphs of the 6 basic trigonometric functions and looking at their properties. So let's start with the graph of sine of x. So there's the graph. We can see that it's on a square scale here. Notice that I have this grid lines or hash marks in multiples of fractions of pi, and then as just integers going up and down. So if I put some certain grid lines on here, now what I'll have is I've got vertical lines at every multiple of pi over 2, and the horizontal lines I've just got at 1 and -1. So there's part of a nice grid for us. So some selective grid lines, and I can zoom in or out. So let me zoom in just a little bit here so we can get a really good look at maybe a couple of periods here. Let's do a couple periods maybe centered up on the axis, something like that. Okay, so the first question that you might want to know about any function is what is its domain? So what x values are allowed? Well, we can see that all real numbers, the x values are allowed. So we can see that as these points on the x-axis. If we project this down on the x-axis, we get the entire axis, which means over here in the unit circle, any point on the unit circle is allowed for our terminal side to go through. In general, what we're going to see on these trig functions is if the function is defined, it's continuous at that point, but there are discontinuities on some of them, not sine and cosine, but the others there have discontinuities, and they occur where the function is undefined. A discontinuity basically is just a break in the graph. So the breaks in the graph happen when the function is undefined, and every time that happens, there's a vertical asymptote. That happens for tangent, secant, cosecant, and cotangent, but not for sine and cosine. So sine and cosine are continuous functions, meaning they're one connected piece. Okay, so the next question is, well, what about the range? Now remember, sine is the y values over here on the unit circle. So when we look at the range, the y values go from -1 to 1, which means that that's the y values that you have here. So if we project onto the y-axis, we see that we're going from -1 to 1 for the range. Okay. Now, what about the y-intercept? Well, since it's defined everywhere, it will have a y-intercept. Being a function, it will either have one y-intercept or none at all. And of course, the sine function is defined at 0, so it does have a y-intercept of y equals 0, the origin, 0, 0. So 0, 0 is the y-intercept. Okay, what about x-intercepts? All right, now things start getting more interesting because we see that it crosses the x-axis at 0, at pi, at 2 pi. Where does it cross the x-axis? Well, it's when y is 0 on the unit circle. That's two values for the terminal side, either pointing straight to the right, here, going through the point 1, 0, or straight to the left, going to the point -1, 0. But that translates to infinitely many different rotational angles that will end up pointing on the x-axis to the right or to the left. And each one of those gives rise to an infinite set of x-intercepts. So the ones that point towards 0 on the axis over here on the unit circle are the ones that are at 0 plus multiples of 2 pi. So this one here at 0, at 2 pi, there'll be one out here at 4 pi, negative 2 pi. And if you notice at those points, the function is increasing, okay, and it crosses the x-axis. Whereas if you're going out to negative pi, or to pi, which is going on the negative part of the x-axis, it goes to the point negative 1, 0. That set of terminal sides will give you these points here at pi, 3 pi, negative pi, the odd multiples of pi. And if you notice at those points, it crosses the axis over here, but it's decreasing as it goes through those points. But anyway, when you put all of those together, you get all multiples of pi, integer multiples of pi for the x-coordinates. Of course, it's an ordered pair for x-intercept. So it is a point, so it has a y-coordinate. Of course, we know the y-coordinate is 0. So in our set notation, that's the set of ordered pairs n times pi, comma 0, such that n is an element of the integers. And we get all of those points there. All right, and so this kind of points out one of the most important things about trig functions is that they're periodic. So the period here is 2 pi. So for example, if we go from 0 to 2 pi, we get one complete cycle here. That's not really surprising because as we go around the circle, 0 to 2 pi takes us all the way around the circle, and after that we're just repeating the same points as we go further and further around the circle, clockwise or counterclockwise. And here we get clockwise, negative, counterclockwise, positive. And so here we see from 0 to 2 pi on the graph, we get one complete period, one cycle, one part of the wave there. And then that just repeats again as we go, say, from 2 pi to 4 pi or 4 pi to 6 pi. In fact, we can start anywhere we want. For example, we could start at minus pi to pi and will give us one complete cycle, ending in the part of the cycle that we started. I do want to mention something else about the x-intercepts before I forget. The x-intercepts are also inflection points. Now let's talk about concavity first, just a minute. This is concave up when y is negative. So any of the times when y is negative, it's what we call concave up. That's basically like a right side up bowl. Okay, so it looks like that. Whereas it's concave down on the y's positive part, like from 0 to pi or from 2 pi to 3 pi, that's when the bowl is upside down. And when a graph changes from a concave up to down or from concave down to concave up, that's called an inflection point or point of inflection. And notice that the x-intercepts are exactly the same as the inflection points. And that's going to be true for all of the trig functions that we look at here. If it is a x-intercept, it will also be an inflection point. So those that have x-intercepts, those x-intercepts are also inflection points, and that's the only inflection points they have. Okay, so that's x-intercepts and inflection points. Now we see the period. Now we also have, in addition to this, we have some local maxima. The local maxima is the highest point in the little neighborhood. These are, in fact, global maxima in this one as well. So these are ordered pairs, and notice the y value is always 1 on them. So I'm talking about the local maximum point, or maxima is plural, low maxima points. But notice where they occur. Well, it occurs first at pi over 2. Well, over here in the unit circle picture, it's whenever the graph is at the highest point, because it's the y value. Well, that occurs exactly one time right here at this terminal side. That's an angle of pi over 2. But of course, we can also get to that terminal side by extra rotations of 2 pi. So if we take pi over 2 plus 2n pi plus 2 pi, we get it 5 pi over 2. Or if we take it and add another 2n pi, we go over here, we're at 9 pi over 2. Or if we subtract 2 pi, we're at negative 3 pi over 2. So all of those points are maximum points. So the x-coordinates are pi over 2 plus 2n pi, such that n is an integer, and the y coordinates are always 1. So here's an ordered pair right here, 2 pi over 2 plus 2n pi, comma 1. If n is 0, we're at pi over 2. If n is at 1, we're at 5 pi over 2, comma 0. If n is negative 1, then you can work out the fraction there, and you see that you're negative 3 pi over 2, comma 1. And so those are the local maximum points, the local maxima. Maximum is singular, maxima is plural. Minimum is singular, minima is plural. So how about the minimum points? So local minima happen here, and where the y value is 0. I mean, where the y value is negative 1. And so that is when the x value is 0 here and y is negative 1 over here on the unit circle picture. That is the lowest y value being the value of the sign over here on the unit circle. And so that happens exactly one terminal side at negative pi over 2, or at 3 pi over 2 if you'd like to go around the positive way. So take either negative pi over 2 or 3 over pi over 2 and add multiples of 2 pi. You will get the x coordinate, the y coordinate being 1 for all your minima points. Okay, and so we see here, I like to take the one closest to the origin, which is negative pi over 2, and add 2n pi to that. It would have been totally fine to say 3 pi over 2 plus 2n pi, comma negative 1. Or for that matter, you could have said, something over here like 7 pi over 2 plus 2n pi. It just makes more sense to either take the negative pi over 2 or the 3 pi over 2. I like to take the negative pi over 2. So that is the set of all minimum points. Now, if you don't care whether it's a maximum or a minimum, you could call it an extremum. And there are all of your extrema right there. Again, extremum is singular, extrema is plural. They're the places where that graph hits 1 or negative 1 on y. Finally, I want to mention symmetry. This is an odd function. It has origin symmetry. An odd function means f of minus x equals opposite of f of x. So if I put in an x value here, whatever this is, I put in the opposite of x here, I get the opposite y. And so you see that, you can see that on the picture here, and that is an origin symmetry here. What that means is if I rotate here by an angle theta, here I rotate by the opposite angle, minus theta, I get points that are vertically the same. That's the same x. But notice that they have the opposite y's. Sine is the y value, so opposite y's means opposite sine values. So f of minus x is opposite of f of x. Over here on the graph, what that means is it has origin symmetry. If I could place my pencil right there and spin this and rotate it, this part here of the wave, for example, would land on top of this part, and this part would land back on top of the part up here. So we have origin symmetry there. So there's kind of everything all at once there. Okay, let's do the same thing for cosine. Okay, once again, the domain is all reals. Everything gets used here on the unit circle. Points, everything gets used on the x-axis here. All reals, there are no asymptotes, no breaks of the graph of any kind. It is a continuous function. All reals are used. What about the range? Same as the sine graph. It goes between negative 1 and 1. You can see that on the grid lines. That's the y-axis there. Those are the y values that are used. That's the range. Notice the square brackets means those are included. If you use round ones, that means you parentheses, you do not include the points. That's interval notation. This is another way of saying x's, set of all x's, they go from the negative 1 is less than or equal to x, which is less than or equal to 1. That's the most compact way to write it. It will have exactly one y-intercept. It is at 0, 1. So you think about cosine starts high and then comes down. Over here on the unit circle, that's y-intercept is when x is 0. Over here, it's where theta is 0. That's on here where x is 1, y is 0. Cosine is the x value, which is 1. So that's why it's 1 here. All right, how about x-intercepts? Well, they are, once again, the inflection points. where it changes from concave up to concave down. Like the sine wave, whenever the graph is above the x-axis, y is positive, it's concave down. And wherever the graph is below the x-axis, that is y is negative, the graph is concave up. It changes exactly where it hits the x-axis. Those are both x-intercepts and inflection points. There are points. We know the ordered pair. We know the y is 0. Let's look at the x values. Okay, well, it's going to happen over here when x is 0 on the unit circle. That's when the graph, the terminal ray is pointing straight up or straight down. One way to get there is pi over 2 to point straight up. One way to get straight down is the negative pi over 2. If we take pi over 2 and add multiples of 2 pi, we get 5 pi over 2, and we also get to negative 3 pi over 2 and infinitely many other things. Those are the places where the graph is decreasing and hitting the x-axis. If we take negative pi over 2, the graph is increasing here and hitting the x-axis, and it's an inflection point. If we add pi over 2 to that, we add 2 pi to that, we're at 3 pi over 2. If we subtract 2 pi from that, we're at negative 5 pi over 2, and so forth. If you put all those together, we actually get pi over 2. Since these are just pi apart and these are pi apart, they're all just pi apart. So a way to sort of simplify that, rather than thinking of it as two sets, there are kind of two sets here because there's two terminal rays here. One set the function's increasing, the other set the function is decreasing. But as far as you just list where it crosses the x-axis, they're all just basically pi over 2 plus multiples of pi, right? So take pi over 2 minus pi, you're at negative pi over 2. That gets you the other one. Take negative pi over 2, subtract pi over 2. We're at negative 3 pi over 2, which is kind of like the pi over 2 again. Take pi over 2 and add pi. We're at 3 pi over 2. So just keep adding multiples of pi, and you get all of them. So here's the bottom line. It's a set of ordered pairs such that the ordered pairs look like pi over 2 plus n pi, comma 0, such that n is an element of the integers. All right, what do you see for the period? Well, once again, it's 2 pi. Again, not too surprising. We get around the circle one time. It's going to repeat the same things over and over again. So here's one part of the way from 0 to 2 pi. And we can see that. That's one period of it. How about extremum? This one also has local maxima and local minima. Let's look at the local maxima first. Maxima are going to happen when the x is the biggest over here in the unit circle picture. That's going to be all the way to the right here at 1, 0 for where the terminal ray. That's an angle of 0, among other things. 2 pi is another way to get there. So it's 0 plus multiples of 2 pi. In other words, just multiples of 2 pi. So it's going to be 0, 2 pi, 4 pi, 6 pi. Also over here at negative 2 pi, negative 4 pi, and so forth. All right, what about the minimum values? And by the way, those maximum values happen when x was 1. Y is 1, excuse me. Y is 1. Local minima happen when y is negative 1 here. That's when the x is furthest to the right here, and that's one way to get there is at pi or at negative pi. So pi or negative pi, and we add multiples of 2 pi to that because of the period that's going on here. Okay, so that's it. Pi plus 2n pi, comma, negative 1. I actually think this is maybe the best way to write it, but another way to write this would be to factor the pi out and write it as 2n plus 1 in parentheses times pi. So another way to say that is an odd multiple of pi. 1 pi, 3 pi, 5 pi, negative 1 pi, negative 3 pi. It's another way to say the same thing. So there's all of the extrema in that case. What about symmetry? Well, this one is symmetric about the y-axis. Again, if we rotate a angle positive theta and we rotate the angle negative theta, these give you the same x vertically. Well, same x means the same value for cosine. So that means the f of the opposite of x is the same as f of x. On this graph, that says if we take a point here, anywhere that we have it, then its mirror image on the other side of the x-axis is another point with the opposite of x but the same y. the same cosine. And so that has mirror image about the y-axis. If I were to reflect this over this part here, on the right side would land on top of the part on the left and vice versa. And so it has mirror image symmetry or reflective symmetry about the y-axis. We call that y-axis symmetry. Here are all those properties listed together. All right, how about tangent? Well, now we get to something interesting when we get to domain, right? Because when we talk about the domain of tangent, it's not everything, right? So when we look at here at the unit circle picture, tangent is y over x. So if x is 0, when it's pointing straight up or straight down, these points have to be removed from possibilities over here on the unit circle because that would be dividing by 0. Well, what angles are those? Well, straight up would be pi over 2, straight down would be minus pi over 2. So we see that this function here has holes in the domain. The domain's the x value, so I projected that down the x-axis. But notice we have holes in that everywhere that in the domain, everywhere we have pi over 2 plus 2 n pi and negative pi over 2 plus 2 n pi, or in other words, pi over 2 plus n pi, odd, or another way to say that is odd multiples of pi over 2, right? Notice that that happens everywhere the cosine is 0 is exactly where the tangent is undefined, and that is the places that we have vertical asymptotes that you can see. So if we say the easiest way to say this funky looking R here is the set of all real numbers, and we want to take away some of those real numbers. We want to take away the ones that look like pi over 2 plus n pi such that n is an element of the integers. So we take those real numbers except for this. This set is the stuff that's not in the domain. We have everything else, all real numbers except for that are the part that is in the domain. Those x values are, if you say x equals those values, those give you vertical asymptotes. Now, a vertical asymptote there is a line. It's a line of the form x equals a constant, and it's x equals these same constants that aren't allowed in the domain. So x equals pi over 2 plus n pi, such that n is an integer, is the set of asymptote. I had an extra parentheses there that I need to remove, so you can see it now like it should be. Just a set of lines. Again, there are infinitely many of them, so we have to write that down some way, and this is the proper way to do it in mathematics, then it's also very compact. Now, what about the range? Well, if you look, all y values are used on the range right here. So that's everything. It does have a y-intercept. Tangent is defined at y equals 0. The x value here is 1, and the y value is 0, and the radius is 1. 1 over 1 is 1. The x value, the y value is, let's see, wait a minute. It's y over x. So y is 0, x is 1. 0 over 1 is 0, and so that means 0, 0 is on the tangent. That is the one and only y-intercept. What about x-intercepts, which also turn out to be inflection points? Okay, and they are, well, you can tell, they're the multiples of pi. Where does that happen? That happens over here when the angle is pointing directly to the right for the terminal side. That would be 0 and 2 pi and 4 pi. But also directly to the left, that would be at pi, negative pi, pi, negative pi, negative 3 pi, positive 3 pi. All right, so if you put those together, you get all multiples of pi, and as we may notice that the period is just pi this time. So we know that if you shift by 2 pi, you're going to get the same thing because that's just going around the unit circle one more extra time. But what we get is a bonus here on tangent and also cotangent, where the period is only pi. So the full pattern is repeated between, say, negative pi over 2 to pi over 2, or any length of any continuous length of pi. That's going to be one period. And so we notice that the reason this works is because when you have rotate an extra pi, you get opposite rays. Opposite rays have both opposite x and y, and those divide out to be the same ratio. Y over x is the same as minus y over minus x, and so they have the same tangent. And so tangent, we get this bonus that the period is only pi instead of 2 pi. Okay. All right, what about local and global minima and maxima? Well, it doesn't have anything. There is no local minimum or maximum here, and certainly no global minimum maximum. The range is all reals. What about concavity? Those x-intercepts are inflection points again, just like we saw with sine and cosine. Notice that in this time, the opposite of sine and cosine, when the y is positive, tangent is concave up, and when y is negative, tangent is concave down, with those x-intercepts being inflection points as well. I do want to show you one extra thing here about another key point when we look at our grid lines here. We notice, of course, the x-intercepts. Be sure if you're graphing, you get those. But I want to show you one special point. When you're looking at if this terminal side is on the line y equals x, that means the tangent is going to be 1 or negative 1. So those are angle. One place that happens is at pi over 4, we get the tangent as 1. So exactly halfway between the uh, x-intercept and the vertical asymptote, there's a place where it hits 1, or on this side, negative 1. So if that happens at pi over 4, of course, it'll happen again at another pi added to that. So that would be 5 pi over 4. And another pi added to that, that would be 9 pi over 4. Or subtract pi would be negative 3 pi over 4. At negative pi over 4, we're at negative 1. So we'd also be at negative 1. Add pi to that would be 3 pi over 4, and so forth. So if you're drawing one of these graphs by hand, these are some key points to get. You want to get the fact that you have it goes to the origin, it goes to the pi over 4, 1, negative pi over 4, 1, concave down, increasing this way. And notice our asymptotes happen exactly where the function is undefined there. One doesn't necessarily need to draw in the asymptotes. You can kind of see that as the graph approaches that. You can see it. You can kind of see the asymptotes because it's approaching it. The asymptotes really are not part of the graph, but they are some nice references if you want to draw them in. Maybe draw them in as dotted or dashed lines like I have here. All right, let's go to secant. Remember that secant is the reciprocal of cosine. So there's a nice relationship here between cosine and secant, and that is when cosine's at a maximum, secant is at a minimum. And vice versa. Okay. So what's the domain here? Let's go ahead and just start there again. Well, it's not just anything. The domain here is all reals except for, well, what? Secant is 1 over x here. So when x is 0, it's undefined. That was the same thing we got for tangent. Same setup. And we're going to have the same asymptotes for tangent and for secant. See that? And what are those x values? Well, they're when x is pi over 2 or minus pi over 2, pointing straight up or pointing straight down, or add multiples of 2 pi to those. That turns out to be, since these are just pi apart, that turns out to be just pi over 2 plus multiples of pi. So those x values, pi over 2 plus n pi, such that n is an integer, are the things that are not in the domain. So the domain is all reals, take away that, all reals except for that. And those x values, x equals those, are vertical lines. X equals pi over 2 plus n pi, such that n is an integer, are the set of all those vertical asymptotes. Okay, so you can kind of see it there. What about the range? Well, it's not all reals. Remember, cosine, its reciprocal, was between 1 and -1. The reciprocals of numbers between 1 and -1 are either bigger than 1 or less than -1, which is so the graph is above y equals 1 or below y equals -1, except at the points where the cosine graph and the sine graph touch, when y equals 1 or y equals -1. Okay, and so those are the local minima and maxima. So let's go over that next. So the minima occur when y is 1. So that's the bottom part of these pieces that are concave up. With part above the x-axis, the y is positive, or each piece is concave up and has a minimum value when y is 1. And what are the x's? Well, they're 0, 2 pi, -2 pi. So they're multiples of 2 pi. So that's the set of ordered pairs 2n pi, comma 1, such that n is an element of the integers. They're ordered pairs because they're points. The y values are 1, but then the x values are 2n pi. Now that's all those guys. How about the minimum values? The local minima occur at the odd multiples of pi, or just pi plus 2n pi, or if you'd rather write that as 2n plus 1 in parentheses times pi. And so those are shifts of pi by 2 pi, or odd multiples of pi, 1 pi, 3 pi, 5 pi, -3 pi. And then, of course, then the y values that go with this are -1. So the set of ordered pairs there is the ordered pairs pi plus 2n pi, comma, -1, such that n is an integer, and that is the set of maxima. So the maximum, notice, is the highest of a bunch of negative numbers at -1, and the minimum y value up here is the lowest of a bunch of positives. Now, it doesn't have a global max or min because it goes up forever and down forever. Also notice that there's this big gap here in the middle between -1 and 1. That's a big gap in the range. So there's a gap right there in the range there. It only has one y-intercept, and it's at 0, 1. It is also one of the local minima. Okay. And what about x-intercepts? Well, it doesn't have any. Doesn't touch the x-axis, and it doesn't have any inflection points. It's all concave up when y is positive, and all concave down when y is negative. This one has y-axis symmetry. It's an even function. The two functions that are even are cosine and secant. The others are odd. If we take any point here and do its opposite x, you get the same y. Looking at the unit circle picture, and again, if you rotate a positive angle and then rotate it by its opposite, you get 2 points with the same x-coordinate. Therefore, their secants are the same. That means you have y-axis symmetry. You have this piece as a mirror image of this. This piece here is a mirror image of that, and so forth. Here are all the properties together in one list or table. One thing we might notice about sine and cosine is that they're just shifts of each other by pi over 2. Okay, and since they're shifts and secant is just above sine of cosine like that, reciprocal, cosecants are reciprocal of sine. We see that secant and cosecant are shifts of each other by pi over 2. So we're going to see a lot of things, similarities between secant and cosecant here. Once again, the domain is not all reals. We have some asymptote. We have some vertical asymptotes. Where do those vertical asymptotes happen? They happen when the function is undefined. Now, let's look at the unit circle picture. Cosecant is 1 over y. So if y is 0, that's when it's pointing straight to the right or straight to the left. That would be an angle of 0 or an angle of pi, among others. Those are places where the function is undefined. Those are pi apart. If you shift either of those by 2 pi, it's just like just getting multiples of pi. 0, pi, 2 pi, 3 pi, -2 pi. So all real numbers except for n times pi, such that n is an integer, would be the stuff that is good, the stuff that is in the domain, the red part here, on the x-axis. The holes in the domain then are at multiples of pi. At each one of those holes in the domain, we have a vertical line that the graph does not touch, and it approaches it asymptotically. So x equals n pi such that n equals, or n is an element of the integers. That set of vertical lines is a set of vertical asymptotes. The range is the same as the range for secant. It's from 1 to infinity and from negative infinity to negative 1. Here's how you write that in interval notation. Parentheses, left parentheses, negative infinity, comma, negative 1, right bracket, union, left bracket, 1, comma, infinity, open bracket on the open parentheses on the right. So notice you can't include infinity or negative infinity, so it has to be a parentheses there, but we do include negative 1 and 1. We do have values with some of the, these values right here have y's of 1 or negative 1, so that is included. Again, maybe we can turn the grid lines on if we want. We can turn these off or on as needed. X-intercepts doesn't have any. Y-intercept doesn't have any of those either. Okay, the period is 2 pi. You go through this, you repeat it from going from 0 to 2 pi, for example, we'll repeat it one time. All right, how about the minimum values? The minimum values on this happen when y is 1, and that happens at pi over 2 plus shifts of that by 2 pi. So pi over 2, 5 pi over 2, what would that be? 9 pi over 2 should be the next one. Yep, there it is. Next one this way would be a negative 3 pi over 2, negative 7 pi over 2. All of them have the same y coordinate of 1. So they're all have the same minimum value. They're all local minima. So those are as ordered pairs. Those are pi over 2 plus 2n pi comma 1, such that n is an element of the integers. Those are minima. How about the maxima? They're down here on the bottom part, the highest of a bunch of negative numbers. The highest one there is negative 1 for the y's on all of them. They are just negative pi over 2 plus shifts of 2 pi. If you'd rather say 3 pi over 2 plus 2n pi, it would be the same thing. So this is the way I like to write it, like this. Just like the cosecant and just like secant, when y is positive, everything's concave up. When y is negative, everything is concave down. Symmetry, it's an odd function. F of the opposite of x is the opposite of f of x. If you put an x in here and then put its opposite, pick an x, put its opposite, you get opposite y's. When this one's negative, this one's positive. When one is positive, the other is negative. So notice that what we have here on the unit circle picture again, when we rotate a positive angle, rotate by the negative of the same angle, we again always get the same x's, but they have opposite y's. Cosecant is based on y, so opposite y's there means opposite cosecants, which is what we see here. Well, what does that mean in terms of symmetry? That means that it has origin symmetry. If we put our pencil at the origin here and spin this around, this part right here would be on top of the part down here and vice versa. The graph would end up being the same thing. So that has origin symmetry, which is 180 degree or pi radian rotational symmetry about the origin. There's all the properties together on that. All right, we just have one more. Cotangent. Notice that cosine and sine are shifts of each other. So secant and cosecant are shifts of each other. However, notice that tangent and cotangent are not shifts of each other. It's actually, they are congruent in some way, but they're what you have to do is you have to flip it over the y-axis and then shift it, and then you get the same thing. Okay. Well, let's do the range first. It's easiest. We see that the range is all reals, just like it is for tangent. How about a y-intercept? Well, it doesn't have one. This one doesn't touch the x-axis, y-axis. So what is the domain of this? Well, cotangent over in the unit circle picture is x over y. So anytime y is 0, you're dividing by 0, and the thing would be undefined. Well, there's only two places that happens on the unit circle. That's right here at 1, 0, and over here at negative 1, 0. That would be an angle of 0 or an angle of pi, among other things, because you could rotate around more times. Okay, so these are the places when y is 0 over here in this picture on the unit circle. Well, what does that translate to over here? Well, it translates to all real numbers except for, well, it's just multiples of pi. 0, pi, 2 pi, 3 pi, negative 2 pi. And we see that so all real numbers minus or take away multiples of multiples of pi is this. So it's all set of all real numbers except for the set of n times pi such that n is an integer. Of course, x equals those values where it's not allowed. X equals n pi will give you vertical lines. These are these dotted vertical lines over here, which are not part of the graph, but they are reference lines where it's getting closer and closer to the graph. I have grid lines already drawn at those points here. The period on this, like the period on pi on tangent, is pi. So this going from 0 to pi picks up one full piece. All the other pieces are just that piece shifted to the right by multiples of pi or to the left by multiples of pi. The x-intercepts are the inflection points. The x-intercepts here are when what happens over here. It's when the cotangent is 0. Cotangent is x over y. It's when x is 0 over here. That is pointed straight up or straight down. Okay, and that gives you the points on the x-axis here. Notice they are inflection points because just like tangent, secant, cosecant, and cotangent, all of them, when y is positive, the function is concave up, and when y is negative, the function is concave down. Where it crosses the x-axis is the inflection point. They are ordered pairs. It crosses the x-axis, so we know the y-coordinate is 0. What about the x-coordinates? Again, they happen at pi over 2 and at negative pi over 2 and at 3 pi over 2 and 5 pi over 2. So it's just pi over 2 plus n pi, comma 0, such that n is an integer. Again, the period is pi, so no surprise when that's just shifting by pi. It doesn't have any maximum or minimum points, and it doesn't have a y-axis, y-intercept, so those are all just none. A couple of key points. In addition to these points where it crosses the x-axis, would be noticing that whenever you go to pi over 4, the right here, y and x are the same, so cotangent is the same numerator denominator, so it's 1. So cotangent of pi over 4 is 1. Cotangent of minus pi over 4 is minus 1. Notice that those are exactly the places where the tangent and the cotangent meet each other. Pi over 4 plus shifts of pi, so that'd be 3 pi over 4. I'm sorry, pi over 4 plus pi would be 5 pi over 4. That would be here. And then add another one that would be 9 pi over 4, which would be here. But they also cross here at negative pi over 4, down here at negative 1 for y, and shift that by pi, you get 3 pi over 4 here, and so forth. So you get a bunch of these things, infinitely many of them. I just pointed out a couple of them there. So if you're going to draw either tangent or cotangent, you want to make sure it goes through those points there. Some key points. How about symmetry? It has y-axis, not y-axis, has origin symmetry. It's an odd function. Okay. If you look at this, again, a positive rotation and a negative rotation by the same amount give you the same x value, but opposite y's. Opposite y's, same x's makes cotangents negative. Makes cotangent opposite of each other. So if I pick this, when this is cotangent's positive, you take the opposite x over here, cotangent's negative, but same absolute value. When the cotangent is negative here, the cotangent of x is negative, cotangent of minus x is positive. So the f of opposite of x is the opposite of f of x. That makes it an odd function. And again, that has origin symmetry. So if we take this and spin it around y equals x, this part here is going to rotate around and land on this part here, and this part's going to rotate around and land on that. So it has that. Here's all those properties together, and now we have summarized all the different ones. So here were the properties of sine, cosine, sine, tangent, secant, cosecant, and cotangent. In my class, I expect my students to memorize all of this, but hopefully you're not just memorizing it, you're memorizing it by understanding what you see on the graphs. Again, graph of cosine, sine, secant with the cosine, sine with the cosecant, tangent with the cotangent, tangent with the secant, same asymptotes, cosecant with the cotangent, same asymptotes. So lots of interesting connections and things about the shapes there.